Cool. So I'll share my screen. This is lecture 5, right? So recap. And by the way, like at the end of the lecture, stay back for say 5-10 minutes or so at 9. Okay, so we defined what a basis is. So basis is essentially, I mean, this picture here. So if you have, well, I'll write in R cube, then this is like the standard basis. This is 1 0 0. This is along the x-axis. This is along the y-axis, and this is along the z-axis. And yeah, so why is this the basis? You kick any one of them out. This is not going to span R cube anymore. So this is like minimally spanning. And if you also observe, this is also linearly independent and spanning. So whatever definition you find convenient to verify here, use it. So we defined the basis, and then we showed all bases have the same cardinality. And then we call this cardinality to be the dimension. Okay. So this is where we were at the end of the previous lecture. Cool. So any questions so far, or should we get started with today's stuff? Okay, cool. We'll move on. So the first thing that we're going to do, or the goal for this lecture or the next two lectures, depending on how much of our time it's going to take, is so we first are going to show that well, our goal was to study abstract spaces, but we'll show that there's no point in studying abstract spaces beyond a point, because we'll actually show all abstract spaces of dimension n over a field k is as good as studying over a field f is as good as studying f to the n over the field f. So instead of looking at a very abstract space, you might as well just work with f to the n, which is far easier to work with. So what we'll actually first show is like all vector spaces are the same up to isomorphism. I'll make these notions like a little more clear as the course of the lecture, but the idea we're going to show is like there's no point working in super abstract spaces beyond a certain point. Okay, so consider V such that dimension of V is n. Okay, and V is over field F. So what we'll do is we'll pick a basis of V. So how many elements will basis have? Not a hard question, but I mean answer this just to know that we are keeping track.
N.
Right. So let B equals I don't know, V1, V2 all the way up till Vn. Okay, cool. So now this is the basis. So if you remember definition 4, of basis, each vector v belonging to V can be expressed uniquely as a linear combination of vectors in B. Okay, this is like one of the four definitions equivalent statements that we had written down yesterday. So what we'll do is like we'll use that fact, and then so we know that V is actually equal to A1 V1 plus so on up till AN Vn. Okay. So now what we'll do is define this map here. So f to the n an. Okay. So is it clear how we are defining this map? So V is actually summation ai vi, I running from 1 to n. So the first question that we need to answer is this a well defined map? And the second question we need to answer is this an isomorphism? Can someone answer 1 and 2 for me? Okay, so do you understand what I mean by a well defined map? So a function is like well defined only if for some point in the domain, like you don't have two images, right? So this is a function essentially.
Yes, sir, because you can get it from the fourth
Just 1 minute,
definition
Raghav.
basis.
Yeah, exactly. So just 1 minute. I'll just tell what I want to do. What exactly I want mean by statement one, and then I'll ask you. Okay. So this parabola is like a function, but this is not a function because this guy has two images here. Okay, this is what I meant by a function being well defined. Yeah. Okay, Raghav. So now give me your argument.
So we can directly get it from the fourth point of the basis definition, so that all a1 and are distinct for any vector v.
Exactly. So this a1 through an is unique for a vector v, or let me put it this way: for a vector v, a1 through an is unique. Which implies there does not exist two images for possible images for phi of b. Which implies phi is well defined. Okay. So the second one is phi and isomorphism.
Sir, it is, I think, definitely subjective, because given any a1, a2, an, we can get a v.
Okay, this is cool.
from V.
So phi is surjective. Who was that, by the way?
Sir Raghav.
Nice. Phi is surjective because for all a1, or to be precise, a1 all the way through an, phi of summation ai running from 1 to n is exactly this vector here, a1 through an. This
What
is
is
good.
VI over here?
Sorry, what?
What is VI?
Oh, okay, so right. So what we did was we began with a basis B of the vector space V. Okay, so we fixed the basis, and then this basis has vectors v1, v2, so on till vn. And given these vectors, we said like any vector v can be expressed as a linear combination of these vectors, that in a unique fashion. And then so a1 through an in some sense is like the unique representation of vector v in terms of v1 through vn. And then what we claim is this mapping v to this linear combination style representation, and the other way, like backside from the linear combination style representation to the vector v. So we are trying to show that there's an isomorphism. Does that clear the question as to what we are trying to do so far?
Yeah.
Okay, good. Okay, so phi
Correct.
is indeed
This is also
surjective.
then injective.
Okay, so why is phi injective?
Sir, because if we have two different, suppose V1, V2
Mm-hmm.
that map to the same A1,
Oh,
A2, AN for contradiction,
v2.
then they would
This
have to
is
be the same vector, which would lead to a contradiction.
right. Let's be little careful. v1 and v2 are elements in the basis, so I'll call it w1 and w2. Okay. But yeah, nice argument. So we have a1, a2, so on till an. So by definition, what we have is, well, w1 is a1 v1 plus so on till an vn, and then w2 is also a1 v1 plus so on till an vn, which will imply w1 equals w2, which implies phi is also injective. Cool. So now can someone prove that phi is an isomorphism, or phi is a homomorphism? So we just showed that phi is a bijection. So we still need to show that phi is a homomorphism. That is, phi preserves addition and multiplication, scalar multiplication.
So that can be directly done because of vector addition and vector multiplication with scalars.
Right. So can you spell the arguments out explicitly for me, Raghav? So what do you need to show?
We need to show that phi of V1 plus V2 or W1
W1
plus
plus W.
W2
Yeah.
is equals to W1 W2.
Equals phi of.
W1 plus W2.
Okay. And why is this
Phi
true?
of W. So phi of W is just suppose A1, A2, AN times V1, V2, VN.
No. What do you mean? A1 A2 in times V1 V2 Vn?
Sir, A1 V1 plus
Ah.
A2 V2.
Okay. 1 plus 1 till A and Vn. Okay.
I can express phi 2 in the same way.
W2 as say B1 V1. So until B and Vn. Okay. Now what do you want me to do?
And then because from the previous part, because of subjectivity, we can find the W1 plus W2. So that phi of W1 plus W2 is basically A1 B1 V1. Yes.
Won't it be phi of W1 plus phi of W2?
Sorry.
Won't it be phi of W1 plus phi of W2?
Which this one? Ah, you're right. No, wait. So
I mean,
I
I
see.
agree the last step.
Yeah, right. This has to be W1 and not phi of W1 and phi of W2. So Raghav, do you see why this has to be W1 and W2?
Yes, sir. Yes.
Yeah, I mean phi of W1 and phi of W2 are elements in F to the n, not elements in the vector space V. So you have given me a vector, or you have given me two vectors. Okay, so this has to be W1 and W2, and this is W1 plus W2. So do you want to finish the argument that you started, Raghav? From here on, it's not like super hard. Like the proof is just here. You just have to spot the proof.
Yes, sir. So,
Mm-hmm.
sir, phi of W1 is then A1 is the A1 column vector A1, A2, AN,
Exactly. So phi of
and phi of
W
W2 is 1, B2.
n and phi of W2 is B1 all the way through Bn.
And
Okay, cool.
if we add them in the vector space in the field n, we can get A1 plus B1 and till AN plus BN.
Right. N plus Bn.
Doesn't phi map a vector, a column vector to the a sum of basis vectors, or is it the other way?
It's the other way, right? So we begin with the vector V in capital V, the vector space, and then depending on how this vector is expressed as a linear combination of the bases, that linear combination is some sense the output. So this column vector is like the range of is in the range of phi. Okay. Does it answer the question?
Yeah.
Okay, cool. Who was that by the way?
Okay.
Okay, nice. Okay, so we showed the first part. We verified the first part of phi being a homomorphism. So what is the second part? Someone.
Multiply by scalar.
Okay, so what do I mean explicitly? What do I have to show here? Just spell out the entire statement for me.
Phi of CW equal to C times phi of W.
Cool. And how do I show this?
I guess you can write it out again that it is A1 B1 plus A2 B2.
Right. Then
And then CW will become C times the whole thing.
CW is CA1V1 plus all the way through CANVN. Cool. Then
And phi of the CW will become CA1 CA2 LCAN. And then
fantastic.
you can take the C out.
Okay. I'll just write it this way. Yeah. Thanks, Omkar. So what we actually have showed here is like, well, phi is a homomorphism and phi is bijective. So phi is indeed an isomorphism. Let me write it, spell it out here. So phi is an isomorphism. So all vector spaces of dimension n over the field F are the same up to isomorphism. So what does this theorem say? So this says like, well, so you give me any two vectors. So you give me any two vector spaces which are of dimension n over the field F. Then these two vector spaces are going to be isomorphic. And why is that a cute result? Because, well, so what we discussed maybe yesterday or a couple of days back. So we said if two vector spaces are isomorphic, then it's just like going to be a relabeling of vectors. So a vector v here will be called vector gamma here. A vector a here will be called vector alpha here. But the way two vectors add, the way these vectors multiply with scalars and so on, is going to be exactly the same. So it is good enough for us to study exactly like one kind of vector space of dimension n, and we don't have to go around studying all different vector spaces over f of dimension n. Okay, so this essentially says like there is exactly one vector space of dimension n which just requires study. Like we don't have to worry about different vector spaces throwing us tons of surprises. Okay, and I mean, we have essentially done with this
So are
proof.
they saying that all vector spaces of dimension n are isomorphic?
Yeah, exactly. Over a given field f. Okay, so you can't change the field and then say like one vector space is isomorphic to the other. So once we fix a field f, all vector spaces of dimension n are isomorphic. Is it cool?
Yeah.
Yeah. I mean, like we have done with most parts of the proof. There's like one very trivial statement that we need to add to what we have discussed so far. Like we know that if v is of dimension n, then this is isomorphic to f to the n. By the way, f to the n has dimension n. Is that clear? Or should we discuss why? Anyone? This is isomorphic to v prime. So now how do we show that v and v prime are isomorphic? Well, so let phi be the isomorphism from v to f to the n, and let pi be the isomorphism from say f to the n to maybe v prime to f to the n. So my isomorphism from v to v prime is going to be say pi inverse of phi. So there is a convenient way of drawing these like maps. It's called commutative diagrams. So we have v. So this means that this is an isomorphism. So this goes to f to the n.
But then why did you have to define pi to be v dash to f to then? Can't you do it the other way?
Oh no, so that is because like we just looked at, I mean the way we defined phi was from this vector space to f to the n, and then we said how to define like by pulling out linear combinations and stuff. I just wanted to stick with it. There's no specific reason. So I mean ideally is because it's an isomorphism, pi is an isomorphism, so we know pi inverse is also an isomorphism by when we discussed this theorem yesterday, I guess. So I could have written pi to be from f to the n to v. There is no worries. Goes to v prime. So which implies v and v prime are isomorphic to each other. Okay. So this is like a really strong statement, right? So this just says don't break your head studying multiple vector spaces. It's sufficient if you study one of each kind, and that is really a good statement to have. Okay, good. So now that we have this, we'll focus more on homomorphisms. Okay, so now what we'll actually try and show is okay. So first statement is stick to f to the n for a moment, right? So let A be a matrix. B 1 A1 2 so until A1 n AN1. No, not AN1. AM1. 1 all the way up to AMN. Okay. So now what I'll do is I'll define this map. I mean, I'll use this matrix A as a map rather than just a matrix. So what A says is, well, give me a vector in f to the n. So Aij belongs to f. This is a map from f to the n going to f to the m, given by A of x is, well, just a fancy way of saying like multiply x with this matrix. Okay, so can someone tell me why this is a linear map or why this is a homomorphism? Maybe I'll,
Taking linear combination of the column space of A, the column vectors of A. So I
right.
think we can easily prove both the conditions for homomorphism, the additivity and scalar multiplication.
Right, but I mean that is okay. But can you make it like explicit? Like this is a very simple argument. So you like yeah, intuition as to why this can be true shouldn't be easier than actually showing why this is true. So like this, all you have to do is like verify the addition and multiplication rules, right? Like ax plus ay is indeed ax plus y, and cax is a times cx. Not a big deal to verify. I'll ask you to verify this if you're lost. Shouldn't be very hard. And even if you're lost, ask people. Like not a very hard statement to understand this. Okay. So now what we have is a matrix A is a linear operator. Okay. So now what we'll actually show is every linear operator is in some sense a matrix A. Okay, so what you'll actually do is like you give me any linear operator, I'll be able to find an associated matrix so that you do matrix multiplication with this, you'll in some sense be able to understand how this operator maps in the underlying vector abstract spaces V and V prime. Okay, cool. So what we'll do, begin with a map phi from V to V prime, and let this the basis for V, let V be of dimension n, and so we have basis B1 all the way through Vn. Okay, so now consider what happens when we look at oh wait oh. So now consider what happens when we apply phi onto V1, V2, so on till Vn. Okay, so we'll call them W1, W2, so on till Wn. And W1 and W2 are all elements of V prime, right? Because we apply phi and then the images in V prime. So we'll call it phi of V1, W2 is phi of V2, so on till Wn is phi of Vn. Oh, we have so much space. Interesting. So now what I'll do is I'll call this matrix W to be W1, W2, so on up till Wn. And for instead of computing phi of V, I'll actually claim this is not a bad notation. So I'll actually claim this is equivalent to computing W times A1, A2, so on till An, where V is actually equal to A1 V1 plus so on till An Vn. And we haven't defined how to do matrix multiplication in this form because, well, W1, W2, so on Wn are not elements of F to the n. These are some abstract vectors in V prime. But given how we learn to multiply, this shouldn't be a deal because we have these vectors W1, W2, so on till Wn, and then we are multiplying them along the column, which means we are taking linear combinations of columns. So this is just A1, W1 plus all the way through A and Wn. Okay. So phi of V is essentially computing this map. So that is what we are going to claim. Or phi of V is actually equal to W times. Just 1 minute, Smithali. I'll write the statement down and I'll come to you. Okay. So W times A1 all the way through AN. Yes, Smithali.
Yes, I wanted to ask, we are considering that the dimension of both the spaces are finite, but when they are infinite, what can we do then?
I mean, how do you pick a basis?
Yes, so we cannot really pick a basis. So does the statement hold true even then?
Actually, it turns out it does. So see, the only problem with when we are dealing with an infinite dimensional space is that we don't know how to pick a basis. But suppose if someone gives us a basis, okay, then all these arguments still continue to hold. In fact, if we have time, we'll actually see how to pick a basis. Okay.
Okay, thank you.
Okay. Cool. Yes. So can someone quickly tell me why both these guys are equivalent? I mean, this is a slightly non-trivial statement because so phi v is like some very interesting linear combination of some n vectors, and then on this side we have phi of v, and this side we have w times a1, a2, so on till an. So it is not necessarily straightforward why both of these are equal, but it's not a very far-fetched argument either. You just have to use the property that phi is a homomorphism, and then we'll get the result. So can someone quickly tell me why this is going to be true?
Is phi the same from the previous question?
Can you spell it out?
I'm asking what phi is.
Oh, so phi is some homomorphism, right? So we begin with some homomorphism phi, and then we realize phi of v1 is w1, phi of v2 is w2, and all the way through like phi of vn is wn for v1 through vn in the basis b. And then what we are saying is like instead of looking at phi of v, we might as well write down these elements v1, v2, so on till vn as column vectors in a matrix, and then multiply this linear combination style representation of v with this matrix, and then it's as good as computing phi. This is the claim. Is the story clear? Who had asked this question? Okay, good. So now can someone tell me why this is true? Why phi of v is actually
Can you
equal to?
like expand the into its linear combination?
Okay, so what should I write here? Phi of
A1 V1 plus A2 V2.
okay, and then what happens?
And then since it is a homomorphism, you can break it up.
Okay, so should I write summation I running from 1 to n? What happens?
It will be AI times phi of Vi.
Okay, and this is
And that is AI Wi.
cool. And why is this equal to this guy here? By definition.
By matrix, yeah.
Exactly. Thanks. Okay. So now what we have actually showed here is so instead of really focusing on phi, we can think of this operator as a matrix, and then we'll do matrix multiplication with w. So the only problem here is now we actually don't know how w looks like either. But see, so early on, like we didn't know how v looked like, and we didn't know how the image space w looked like. But now in some sense we have transformed the domain into an element of f to the n, which we actually know how it looks like. Okay, so now what we'll do is we'll go one more step and then try to transform this matrix w into something that we are once again familiar with. So we'll actually make it look like a matrix in f to the m cross n. Okay, so the next goal, make w look like
Trying to show that any homomorphism is just multiplying by matrix.
exactly. Okay, so once again the idea is like this. Okay, let v prime have dimension m. Yeah, go on.
So sir, we need to show that each of the w1, w2, wn are indeed vectors of dimension m, right? Column vectors of size n.
You mean for the previous claim or for this claim?
No, we have to show that matrix. We have to make w look like a matrix m by n. right?
Right.
But we have shown that W is basically W1, W2, Wn.
Right.
So if we can show that each of Wi is a column vector of size m,
Mm-hmm.
then we would be done, right?
Right. So the only problem here is like W can be any vector space, right? It need not be F to them. Or sorry, V prime can be any
Yes.
vector space. It need not be F to them. But we just showed something earlier, right? So if V prime is actually of dimension M, then in some sense V prime is as good as F to them. So this is the intuition that we are going to use, and then we are going to force this matrix W to look like a matrix in F to the M rather than look like a matrix in V prime. Okay. So W1, W2, so on till Wn aren't like already in F to the M, but we'll actually have to force it, and then we'll make it look at make it look like as if it's like in F to the M. Does it answer your question, Raghav? And does it make it clear as to what we are trying to achieve at the end of all this?
Yes. So it
Okay.
is not actually in a matrix of the form M, but we are going to try to.
No, no, your voice is breaking. You'll have to repeat once.
So it is not actually a matrix. Right?
No, it's like really hard to hear you, Raghav.
It's is it an? I'm saying that it is not actually a matrix
Right.
on my
W's.
end, right?
Yeah, W is not at a matrix. If that is your question, right? Is it fine? Is it all right? Okay, cool. So now look at V prime and let V prime have dimension M. So look at a basis B prime equals, I don't know, can someone suggest me an alphabet? Oh man, okay, fine. So we have, sorry? So let B1, B prime be x1 through xm. So now that this has dimension m, and then we can pick a basis of with m vectors. So once again we know that v prime is actually isomorphic to f to the m because v prime has dimension m, right? And in fact these vectors w1 is actually like a linear combination of these vectors here. So we'll call it alpha 1 1 x1 plus alpha 2 1 x2 plus so on up till alpha m1 xm, and then you look at w2, call it alpha 1 2 x1 plus alpha 2 2 x2 plus so on up till alpha m2 xm, and all the way up to wm, or sorry, there is wn, right? Yeah,
Then aren't we done now?
almost. I mean, so now we just have to identify that this matrix of alphas is actually the matrix that we are interested in. But once we do that, we are done. So what is this guy going to be? So it's going to be alpha 1 n x1 plus alpha 2 n x2
But then
plus
this
on.
matrix may change depending on what basis you use.
Exactly. So this basis computation is not canonical in that sense. So these depend on your choice of basis. But then what you can actually do is like you can play around with multiple choices of bases, right? So you can change from basis A to basis B for V, and then you'll get a different matrix. But you'll have to read that matrix in a different way. So given the way in which this maps a vector in V to V prime, you'll actually have to read it slightly differently. But yeah, that's a nice observation that this map depends on the basis that you choose, and such maps are called non-canonical. A canonical map is a map that does not depend on the choice of the basis. Okay, that's a nice point. Who made it? Sorry. Ah, nice point, Omkar. Okay, good. So now instead of multiplying w times a1 through an, instead of w times a1 so until an, so what we'll do is like we'll, if like you look at this map pi between v prime to f to the m, which defined the isomorphism between v prime and f to the m. So this is like that. You take a vector w and then you apply pi. You will get these components, this alpha 1 2 and all those components. Okay, so now look at this matrix A given by x11, not x11, sorry, alpha 11, alpha 12, so until alpha n1, alpha 21, alpha 22. Oh wait, something's wrong. Okay, I think it's right. Yeah, so it's alpha 11, alpha 12, so until alpha 1n, alpha 21, alpha 22, so until alpha 2n, all the way up till alpha m1, alpha m2, all the way till alpha mn. And then you multiply this with a1, a2, so on till n. What do you get? So we get a1 times this vector, alpha 11, alpha 21, so until alpha m1, plus alpha 2 times, sorry, a2 times alpha 1 2, alpha 2 2, so until alpha m2, plus so on up till alpha n times alpha 1n, so until alpha mn. But then look at what happens when we look at pi inverse of this guy here. So pi inverse is also an isomorphism. So these guys will separate out nicely. So we'll get a1 times pi inverse of alpha 1 1 so until alpha m1 plus a2 times pi inverse of alpha 1 2 so until alpha m2 plus so on up till.
So pi is also an isomorphism.
Yeah, exactly. So we showed that yesterday, right? So if pi is an isomorphism, then pi inverse is also an isomorphism, right? I think we showed that a couple of days back. Is it fine?
Yeah.
Okay. And alpha 1n so until alpha, what is it, mn. But then what does the like the inverse image of all these guys? This is just w1 w2 so until wn, right? This is just a1 w1 plus so until an wn, which is exactly w times a1 through an. So now what we actually did is like we made use of a couple of homomorphisms here. So I'll draw this diagram here. So we began with v prime, and then we want a map psi going to v prime. So how did we define this map? So well, we first use this isomorphism from v to v prime, sorry, v to f to the n, and this is like the map phi. And then there is this isomorphism from f to the m to v, or f to the m to v prime. This is also an isomorphism, and this is like pi inverse. And then we look at this. This is the matrix A. Okay. So in order to get this map psi from v to v prime, we made use of these isomorphisms. So apply phi, go to f to the n, use this matrix, and then go to f to the m, and then use pi inverse to go back to v prime. So in particular, so if you think of it this way, right? So phi is like a non-canonical map which just says f to the n is the same as v. and pi inverse is a non-canonical map which says f to the m is the same as v prime. So the only interesting map here, like the only part of this map which defines psi uniquely is this matrix A. So which implies, in some sense, all linear operators are actually matrices.
Wait, what is the
Sir, can you
linear
go
operator?
over the part?
Sorry, one at a time, Raghav.
Sir, can you go over the part where we defined a concept
Okay,
and
sure.
structure?
Yeah, I'll do that. Sai?
What exactly?
No, I can't hear you at all. I mean, is there something at my end, or is Sai's voice breaking?
Is it
No. So, Sai, maybe just put your question in chat. I'll answer Raghav's question and then I'll come to you, okay? So A is this matrix, right? So if W1, like so look at pi. If pi maps W1 to alpha 1 1 alpha 2 1 so on to alpha m1, the first column of A is this guy alpha 1 1 alpha 2 1 so on to alpha m1. If pi maps W2 to alpha 1 2 alpha 2 2 so on to alpha m2, then the first column, so the second column of A is going to be alpha 1 2 alpha 2 2 so on to alpha m2, and then so on. So in some sense, so we had this matrix or matrix-like structure W, which had W1, W2, so on till Wn as its under quotes columns, because W1 is not essentially a column vector. But then what did we do here? We did a very straightforward thing, right? So we wanted W1 to look like a column vector, and then we know that there is a very nice way to make W1 look like a column vector, which is make use of this isomorphism between V prime and f to the m, where elements of f to the m are actually a column vector. So whatever the image of W1 is in f to the m, put that column vector in instead of W1. And whatever W2 corresponds to in f to the m, put that column vector in instead of W2. So we are forcing W to look like a matrix, or we are forcing W1, W2, so on to Wn to look like column vectors. And once we do that, we get this matrix A, okay?
Yes.
Okay, Sai, what was your question?
He asked how do we define a linear operator?
Oh, linear operators are essentially homomorphisms. Like there's just a different name for homomorphisms. I mean, we could have called it linear operators all along, but yeah, we want to be like mathematicians who just try to define way too much notation just to ensure people outside the league can't come in. Okay, so now what we actually showed is for every linear operator phi there is a matrix multiplication, like there's a matrix which corresponds to this. Okay, in fact, fix a basis B of V. V and basis B tilde of V prime, which implies these maps phi and pi are forced now. Like this mapping V to f to the m and V prime to f to the m. So these are forced. Like these are now there's no choice on choosing phi and pi now. Are well defined now. Okay. So now what we'll do is we'll define an isomorphism between phi and A. Okay. So remember, this we defined capital psi. This is not standard notation, but we just like define capital psi to be the set of all phi from V to V prime, such that phi is a homomorphism. Oh, I have to be precise with my notation here. We already used 5 before. So we'll call it like the set of all psi's from V to V prime, so that psi is a homomorphism. And we had proved that this is a vector space. We either proved this or had given this as an assignment. Something of the sort happened. So this is a vector space. And this, if this is a vector space, then this will have a dimension, right? It's either finite dimensional or infinite dimensional or whatever. So now we will try to figure out the dimension of this vector space. So theorem, psi is isomorphic to f m cross n. Wait, f cross n, right? How many columns are there? N columns and m rows, right? Yeah, n columns and m rows. And why is psi isomorphic to f to the m cross n? Anyone want to give a shot? This is a slightly non-trivial statement, okay? So if you want to understand the proof of this, look at this diagram here, this commutative diagram.
What does the diagram represent?
See, so this diagram says like the map psi maps vectors from V to V prime. Okay, but instead of this map psi, what this says is like, apply phi first. Just 1 minute, Smithali, okay? So we apply phi first, then apply this matrix multiplication A, and then apply pi inverse. So now, like this process here, this blue process is the same as this red process. So in some sense, the arrows commute here, right? So it's called a commutative diagram, and this is what this diagram essentially means. Applying psi is the same as applying these three guys in order. Okay, does it answer the question?
Yeah.
Okay. Smithali, yes, your
Yes,
question.
I was saying we can say that psi is isomorphic. For proving that, it is equivalent to say that phi A and pi inverse are isomorphic.
Wait. Psi and A inverse are isomorphic. What was the statement again?
For proving that psi is isomorphic, it is equivalent to say that phi A and pi inverse are isomorphic.
Okay, it's the right direction. So essentially what we'll show is like we need to produce a map from elements in psi to elements in f to the m cross n, right? So the map is just this. So it's way too many alphabets here. So use alpha. First from capital psi to f to the m cross n. So what this guy says is, look at psi. Psi can be represented in some sense uniquely as phi A pi inverse once we fix pi and phi. Okay. So alpha of psi equals A, where psi is actually equal to phi A pi inverse, or sorry, the other way around. Pi inverse A phi. Okay, so first thing is this is a bijection. And why is this a bijection? Well, see, phi and pi inverse are isomorphisms. Phi and pi inverse are isomorphisms. So which means like once you give a vector in here, like you can actually invert phi and pi inverse. So which means if you give psi, there is a unique A for which psi is actually equal to pi inverse A phi. In fact, we actually know how to compute A given psi because that is the exact process that we did to arrive to this matrix A, right? So we were given this operator, this linear map to begin with, and then we try to knock out this abstract space from the domain, and then we knocked out this abstract space from the range, and then we got this matrix here. And this is like we kind of forced all the steps in our construction. So given a psi, like A is well defined, and once you have A, cool. So once you have A, you can construct psi by pi inverse A phi, or yeah, let me put it this way: compose phi inverse on the right and pi on this side. Pi psi phi inverse
Inside that
equals
alpha, is that a psi or a phi?
psi. I mean, phi is this forced map, right? So this is like some arbitrary linear map psi. So this is a bijection because what? Pi psi phi inverse equals A, and pi inverse A phi equals psi. So given psi, like we know exactly how to find the matrix of psi, and given the matrix of psi, we know exactly how to find the operator psi. So alpha is a bijection. Is it fine? Folks, is it fine?
Yes.
Okay, good. So now we'll show alpha is a homomorphism.
I guess Sai is asking how do we find pi and psi.
Oh, so pi and phi are determined by the bases, right? So once we are given these bases b and b tilde, so we know how to use these bases to construct this isomorphism between b and f to the n, and v prime and f to the m. So this isomorphism between v and f to the n, v prime and f to the m, this uniquely defines phi and pi. Once we fix the bases b and b tilde. Does it answer the question, Sai?
How do we get,
No, your voice broke.
how do we get P and P tilde?
Oh, b and b tilde, like pick two arbitrary bases. So we are doing all this computation once you fix these bases b and b tilde. Okay, b be any basis of v, b tilde be any basis of v prime. Is that good? So once we fix these bases b and b tilde, we are doing all our theory based on built around these bases. So we keep these bases constant, and then we are building everything around it. Okay, is that good, Sai?
Yeah.
Okay, good. So now we want to show that alpha is a homomorphism. Can someone help me out with this? So 1 alpha of psi plus psi prime equals alpha of psi plus alpha of psi prime. Can someone tell me why? This is not very hard again if you understand the definitions of pi, psi and phi inverse, and how you add two operators and so on. So this is more like a test of definition rather than how comfortable you are with definitions rather than some fancy clever stuff. Anyone wants to have a shot? And see, we actually very explicitly constructed alpha here. So in fact, alpha of psi is actually equal to pi psi phi inverse. Okay, so given this explicit construction, try and figure out how to do this.
How did you get that?
Sorry.
How did you get that alpha of psi?
So this is from this commutative diagram. So remember how we constructed A. So A was essentially, a nice way to represent psi as a matrix. So what did we do? We used phi to send this vector v to f to the n, used A to send that to f to the m, and then used pi inverse to send that to v prime. So the definition of psi is like, like the composition of these three functions. Is it clear? I mean, that's exactly how we try to construct A. The reason we were trying to construct A is trying to represent psi as a matrix rather than some very abstract linear operator hanging out somewhere in space.
But then how does alpha of psi become equal to this?
See, so what is alpha of psi? So alpha of psi is A.
Yeah.
Okay. And what exactly is psi? Psi is just the composition of these three operators. Do you agree to this? I mean, instead of psi, we are representing psi as phi A pi inverse. Do you agree? Okay. So psi is where are we? So psi is pi inverse A phi. Apply pi on both sides. So you'll get pi psi equals A phi. Pi psi equals A phi. Apply phi inverse on both sides. So you'll get A equals A, which is exactly alpha of psi. Does this make sense?
Yeah.
I mean, are you sure? You don't sound convinced.
Yeah, it's right.
Okay, good. So now can someone tell me, why this is, like this guy here is true? Why this is true?
Alpha of psi equals pi of psi alpha pi inverse.
No, say once again your voice is like, breaking a lot. I mean, I really can't make out what you're trying to say.
Alpha of psi equals pi psi inverse.
Okay, so alpha of psi is pi psi phi inverse. Good. And
And similarly for psi prime. This
prime phi inverse. Okay.
so we just add maybe
No. No, say I can't understand what you're
Sir,
saying. So maybe I'll go to Raghav. Yeah, yes, Raghav.
sir, for given, sir, if we have a different psi, won't there be different alphas and pi's also?
So you mean like for a different basis whether alpha will be different? Is that your question?
No, sir, I am asking for different size.
Huh?
Won't there be different alphas? Sorry, phi's and pi's.
Oh, phi's and pi's. Okay, so let's look at how we defined pi and psi here, right? So this map phi maps v to f to the n. This map has nothing to do with the operator psi or the matrix A. Like we did this construction without even worrying about phi, psi and A.
So, sir,
And
it
then
is fixed with the basis.
yeah, it's fixed with the basis. Nothing to do with this operator psi and A.
Okay. So, sir, only A varies with psi.
Yeah, so the only like the only thing that are not fixed in this commutative maps are this psi and A. And once you pick psi, A is also fixed, and the other way around. Okay. I'll repeat. So this construction of phi and pi had nothing to do with these maps psi and A. We did this construction way before we started we started considering these homomorphisms psi and trying to get a matrix representation of it. We constructed this phi when we actually tried to show all vector spaces of dimension n are the same over a field f.
Okay, sir.
Okay. So we begin with that construction phi and pi, and given that we want to say, okay, how do we represent psi as a matrix A? Cool.
Yes.
Okay. So I'll finish this proof here. So look at alpha psi, we get pi psi phi inverse, and then look at alpha psi prime, which is pi psi prime phi inverse. Now look at alpha psi plus psi prime, which is pi psi plus psi prime phi inverse, which by definition is pi phi phi inverse plus pi psi prime phi inverse, which is alpha of psi plus alpha of psi prime. So we checked addition.
Basically,
No, Raghav, I
yes.
can't hear you. Yeah, go on, go on. I'll see if I can hear you.
So basically, alpha is the function that gives us a for a given psi.
Yeah, exactly. So once you're given a psi, this the map alpha says, okay, for this psi, this is the matrix A. This for psi prime, this is the matrix B. Right? So this is the map.
Yes,
So, okay, is that fine?
yes, sir.
Okay. So what I'll do as usual is like, leave you to check scalar multiplication part. Or maybe why not, I'll just do it. Okay, so now we will have c times alpha of psi, which is c times pi psi phi inverse. But then all of these are linear operators. So c will go inside and outside this linear operator. So I'll just pull c inside. C psi phi inverse. Because pi psi and phi inverse are all linear. Okay, but this is precisely alpha of c psi. Okay, so even scalar multiplication holds good. So which means alpha is indeed a homomorphism. And on top of that, we had already proved that alpha is a bijection. And we actually know how to explicitly compute alpha. Alpha is just like, two isomorphisms multiplied on either sides of psi. Yes. What is this guy? This is like pi psi phi inverse. This implies alpha is isomorphic to sorry. This implies alpha is an isomorphism which in turn implies the vector space psi of all homomorphisms is isomorphic to f m cross n. Okay, so what we have essentially proved here is like, okay, so we said all vector spaces of dimension n is the same as f to the n. Okay, this statement says, okay, all linear operators mapping a vector space of dimension n to a vector space of dimension m is the same as f to the m cross n, which implies, in fact, this is a non-trivial statement which we have actually proved. So, theorem, dimension of psi is actually equal to dimension of f to the m cross n. Proof follows from the fact that psi and f to the m cross n are isomorphic. Is this good, folks? Yes, no, maybe.
Yes.
So a couple more yeses and then I'll take that to be a representative answer. Okay, good. So now can someone tell me what the dimension of psi is then?
M into N.
Exactly. Yes, Raghav?
No, select different dimension.
No, what? Can you type it up? It's like super hard for me to hear you. If it's not like so very long or something. Oh, I see. Okay. So now what is the dimension of psi? To compute the dimension of psi, we just need to compute the dimension of m cross n. So what is the dimension of m cross n? Sorry, dimension of f to the m cross n. I claim this is a basis. So call aij to be, so everything else is 0 except for the ijth element, which is 1. So then I claim that this is a basis. So b equals aij for all 1 less than or equal to I less than or equal to n, and 1 less than or equal to j less than or equal to m. So we claim I claim that this set of matrices, which actually has like 1 in exactly one coordinate and zeros everywhere else. So I claim that this is a basis for f to the m cross n. So can someone quickly give me a proof?
So any matrix we can find the we have a plus b. It's that you have said by multiplying with a1 times like with a1 1, a1 2, a1 2 and so on.
Right. So just give me 1 minute. I'll just put my laptop on charge. I think I didn't get their entire argument, but I just like got a couple of. I mean, I just got what you're trying to say in a couple of places, and I think that was. I mean, you are on the right track. So what Sai at least tried to say was this. Okay, so look at this matrix here. So look at A, which is A11, A12, so on up till A1n, A21, so on till A2n, AM1, so on till AMN. Okay, so what we have to show is like we want to show that this like is spanned by our set B. And how is this a linear combination of vectors in set B? This is just, what is that? A11 times 1 and then all zeros. Plus A21 times 0, 1 here, and then all other folks are zeros. And in general, it just says, you look at Aij. Okay. Oh, sorry, I think I messed up here. This is like the J comma. Oh no, it's fine, I think. So this will be M, so it's row comma column. Right, so this is, Aij is like it just has, 1 in the ith row jth column. So this is like 0, 0, 0.
Just like the standard basis.
Yeah, exactly. This is indeed the standard basis for matrices. I comma jth element plus 1. And if you notice, because like the only place where the I comma jth element can be non-zero is like in Aij times the non-zeroth place. So you'll actually get. And it's easy to verify that we add all this up. We'll actually get A11, A1, 2, and so on. That we'll get the matrix A back, because the multiplication is not super hard. It's like the first matrix gives you A11 and then everything else is 0. The second matrix gives you A12 and then everything else is 0, and then so on. So this says that our set here B, it spans f m cross n. So span of B is indeed Fm cross n, and it is not hard to see that this is the minimal, or it is not hard to see that B is linearly independent, because, well, like every element of B has a unique coordinate where there is a 1. So there is no way like Aij can be expressed as a linear combination of other vectors in B. Okay. I mean, this shouldn't be super hard to see, so I'll maybe leave it as an exercise if you have not seen it already. B is linearly independent. In fact, this is the same as saying that this vector, this bunch of vectors here, 1 0 0, 0 1 0, and 0 0 1. It is the same as saying like these three vectors are linearly independent. Instead of vectors, they look in the matrix form. That is all. Okay, good. So now what we have, B is like B spans after the M cross n, and B is linearly independent, which implies B is actually a basis. And then cardinality of B is M cross n. Why is it M cross n? Well, like we have one matrix for every element ij, and then there are M cross n, for every coordinate I comma j, we have one matrix in B. And then for there are M cross n coordinates. So cardinality of M is M cross n, which implies dimension of F to the M cross n is M cross n. And I mean, why did we do all this? Like we have dimension of psi is actually equal to M cross n. If when psi maps V to V prime, this guy has a dimension n, and this has dimension m. Okay. So the big takeaway from this lecture is essentially saying, well, all vector spaces of the same of dimension n are the same up to isomorphism, and these set of the vector space of linear operators are actually the set of all matrices. So these are like two big takeaways from this lecture. So now what we'll do is like someone asked me about infinite dimensional vector spaces. So I'll define some notation and then we'll stop. Okay. Good. Okay. So now what? Okay. Are there any questions so far? If there are questions, I'll take them. Otherwise, we'll move on with infinite dimensional vector spaces. So I'll pause for a minute just to take questions.
Can we somehow, like, matrices are two-dimensional? Can we somehow generalize this and come up with multi-dimensional homomorphisms?
Multi-dimensional homomorphisms. I mean, think of it this way, right? If you look at an operator that maps the set of operators on V to a set of operators on V prime, for instance, and that will actually look like maybe it will look like a three-dimensional matrix, I guess. I don't know. I mean, why don't you verify that and then let me know. Okay, so think of if you have a three-dimensional matrix, like you will actually have to multiply that along the column by a matrix rather than a vector. So if you're multiplying along with
breaking.
So go on, Omkar.
Your voice is breaking to me.
Oh, is it the case for everyone else, or is it just for Omkar?
We can hear you fine.
Yes, we can hear you clearly.
Oh, okay. So I think it's in your end, Omkar. So I'll just repeat what I'm saying, just for the benefit of Omkar if he has missed this. So, see, so essentially, if we have something like a three-dimensional matrix as psi wants, and we try to multiply along, I mean, the column is not the right word here because it's three-dimensional. So if we try to multiply along the xy side of the three-dimensional matrix, So we are multiplying this three-dimensional matrix with a two-dimensional matrix. So the input to that in some sense must be a matrix, and we just associated matrix with operators. So this might happen when you try to match operators from one space to operators in a different space, maybe. So try to think about it and then see if this intuition helps. And if you actually, if it helps, then yeah, well, so it's nice. Like you might want to discuss this in the tutorial with others.
Okay.
Are there any other questions? And obviously, you can also ask me in the lecture if you're caught up. Okay. Cool. Any other questions, folks? Okay, good. So now, for the moment, take this example of f to the n. Okay. So look at an element in f to the n. How will an element here look like? It will have a1, a2, so on till an. Where a1 through an are elements of f. Belong to f. Okay. So this is something that we have all used, right? So if we are looking at r square, and then we say, hey, okay, 1 comma 2 belongs to r square, good for us. What is 1 in it? 1 is the first coordinate, 2 is the second coordinate. Okay, so in some sense, instead of talking about 1 comma 2 as like pure vectors, we kind of break it down into two parts and then say, okay, this is the horizontal axis, this is the vertical axis. 1 is the component of 1 comma 2 along the horizontal, and 2 is the component of 1 comma 2 along the vertical. So trying to represent this as coordinates is essentially saying this, right? So look at the bunch of all functions f from the set 1 comma 2 to real numbers. Okay, and then if f of 1 is root 2, f of 2 is pi, then this is like saying okay, well, look at this vector root 2 comma pi, whose first coordinate is root 2 and then the second coordinate is pi. Does this make sense? How we associate a vector with a function rather than thinking of it as just a full vector. Okay, so just to be, just to make it a little more general, just to ensure all of us are on the same page. So to represent f to the m or f to the n, so now we'll look at this function f from 1 to so on till n and map it onto f. Okay, so if we have f of 1 is a1, f of 2 is a2, so on till f of n is an. This corresponds to the vector a1, a2, so on till an. So this way of writing stuff essentially says, okay, instead of looking at the vector as a whole, it's the usual coordinate way of addressing things. So we just say first coordinate, second coordinate, all the way to nth coordinate. Okay. So instead of writing f to the n, so let me call this f to the 1, 2, so on till n. And what is this going to be? This is the bunch of all functions f such that f goes from 1 to all the way through n to f. Okay. So instead of calling this pair as f to the n, I'll call this f to the set 1 through n. And then what does this set represent? This set represents how to address each coordinate. So this is essentially saying like this is thinking of just coordinates of a vector space. I'm just repeating this multiple times just so that we get comfortable with this. Okay, is this definition fine?
Can you give an example? I'm not entirely clear.
Okay, so look at this, right? So what does this an element of this set tell us, right? So an element of this set essentially says, okay, f of 1 is this element a1, f of 2 is this element a2, and then we'll look at the set 1 comma 2 for the moment. So n equals 2. So this corresponds to the vector a1 a2. and then you give me a1, a2, I'll be able to define a function f of 1 to be a1 and f of 2 to be a2. I'm essentially saying, given a vector a1, a2, the first coordinate is a1, the second coordinate is a2. This is all I'm saying here. And as soon as I talk about, sorry, say,
I think I got it.
okay. So as soon as I start talking about the first coordinate and second coordinate, there is no necessity to me talk about n as a number, but I'll rather talk about this as a set of 1, 2, so on till n. And then I'm saying the first coordinate is a1, the second coordinate is a2, and so on till an. Okay, and where does this set come? This is like going to be the domain of this function. This just says the first coordinate, second coordinate, so on till nth coordinate. Okay, and as soon as we define the domain this way, there is no need that we actually have to have this domain as 1, 2, so on till n. We can have the horse coordinate and the elephant coordinate. Okay, so this is as good, right? So f square is the same as f of horse comma elephant, where f of horse to f. And then how do we map stuff here? So we get the for a1 comma a2, the map is going to be f of horse equals a1 and f of elephant equal a2. Okay, so as soon as I write a set on top, there is no necessity that this set has to be just a subset of natural numbers or the first 10 natural numbers. We can write any set on top. Okay, so why do we want to write horse comma elephant instead of 1 comma 2? Well, it does no good for us. But where does this actually do us good? I can talk about vector spaces of this kind, f to the natural numbers. So this is an infinite dimensional vector space. And then how do we represent this? This is the collection of all f such that f is from natural numbers to real numbers. And then how will an element here looks like? It will just say f of 1 equals not real numbers, sorry.
How do we know that which element to take first from the set?
What do you mean by which element do we take first?
Like, since the set is unordered, you may take any element first.
Nice question. So in fact, the order really doesn't matter, right? So if I just give you a function f, does the does how I represent this function really matter to you anymore? So instead of saying 1 comma 2 as 1 being the first coordinate and 2 being the second coordinate, overnight if people decide that we'll write 2 comma 1 like the y coordinate first and x coordinate next, does things really matter? Now the plane will just look flipped, but the vector 2 comma 1 with y coordinate first and x coordinate second is the same as 1 comma 2 with x coordinate first and y coordinate second, right? So the fact that the first coordinate is 1 and the second coordinate is 2, like that is the only important thing, and the order in which we represent our coordinates is not at all important. Does that make sense, or am I vague? I'll repeat if that is vague.
Yeah, it's fine.
Okay, so as soon as I get this function f, I don't have to write this function f as f of 1, f of 2, f of 3 and so on. This function essentially says give me some input and then I'll give you the rth coordinate if your input is r. Okay, just for convenience, because natural numbers have a natural ordering on them, I'm just writing f of 1, f of 2, f of 3. There is no other reason why I write it this way. Okay, so if f of 1 is a1, f of 2 is a2 and then so on, then this is the same as this, I don't know, this vector space of dimension n. This we look at this vector a1, a2, a3, blah blah blah. Okay, so do you understand the power of writing f to the n instead of f to the set instead of f to the natural number? Okay, if there is any question, I'll repeat. Okay, so how will f to the real numbers look like? So this is just the bunch of all f from reals to f. And this is slightly harder to represent. So you can't write f of 1, f of 2 and then so on because you want to enumerate all real numbers. So instead we'll use this representation. F of alpha for all alpha belonging to reals. And you see what we are achieving here, right? There is no way I can write this down like, this vector here. I can't enumerate this and then say, hey, a1, a2, a3, and so on. So there is this classic result which actually says you can't enumerate all real numbers like one after the other. So what we have essentially done here is this definition allows us to handle vector space of dimension equal to the cardinality of real numbers, which we couldn't have otherwise handled with the definition of the form f to the k for some natural number k. So this allows us to handle infinite dimensional vector spaces. So that is why we are focusing on f to the set rather than f to the a number. Okay, is this good? Are these definitions good? If these definitions are good, I'll just define how linear combinations in infinite dimensional spaces look like, and then we'll conclude with the summary.
Okay, I am still confused. Why can't we just say f goes from real numbers to a field?
No, sorry, why can't we say?
Why can't we just say f is from R to F? Why do we need f to the R? Oh wait, okay, so f to the R is okay, I got it.
Mm-hmm. No, but I didn't get your confusion either. Can you repeat it if you think that will be helpful to the class?
Okay, so I was just asking why can't we just say f is from real numbers to f, like big F?
Capital level.
Yeah,
So did we just say that?
yeah, that we did. But then I realized that I thought we were saying f is from f to the R to f, but f to the R is just the set of all functions that go.
Right, right, okay. Mm-hmm. Okay, cool. So how do we take linear combinations in infinite dimensional vector spaces, or if there are infinitely many vectors, how do we take linear combinations? Taking linear combinations. I think this is something that you have done so far without explicitly defining though. But this is a good place to make it explicit.
How will you take any real number?
What do you mean by that, Omkar?
Like if you'll have to define it though, right? Like for example, if like there is a countable number of coordinates, but this provides input that is uncountable.
Yeah, exactly. So this vector space here doesn't have a representation of this form in this coordinate-ish way, or we can't really write it as a1, a2, a3, and then make it and look like some the typical r square, or we can't make it look like vectors in there. But we can still talk about these as vectors. Do you agree?
But then if it was like naturals, then we would be able to write it as that.
Yeah, right. So the even till here, like till here, when we defined f to the natural numbers, we were actually able to write a representation of this form.
Yeah.
Okay, but as soon as we went to f to the r, we were not able to get a representation of this form. But we still have a representation of this form, and we can do linear algebra with this set.
Okay, got it.
Okay, so the idea of doing this is so that you actually have something more powerful. This is not just a different way of putting what we had before with the same power. Okay, so the fact that this representation doesn't help us, this a1, a2, so on till a3, so on till an representation doesn't help us, and then but this representation of f to the set helps us, is actually a strength of this definition, right, rather than a weakness. Does it help, Omkar?
Yeah.
Okay, good. So we have not yet proved that an infinite dimensional vector space has a basis, but suppose someone gives us a basis, okay? Now this basis is not going to have a finite cardinality, it's going to have an infinite cardinality obviously, because the vector space is infinite dimensional. So we call this Vi for some indexing set I. So if the dimension of this is the cardinality of real numbers, this indexing set will be real numbers, for we'll say Vi for I belonging to reals. Okay. So this just says, a fancy way of writing, okay, look at the basis. I can't explicitly write this basis as V1, V2, so on, because it need not be, this basis may not be enumerable. But we'll represent this basis like this, okay. So how to take a linear combination of vectors in this B, of vectors in this basis? Well, so linear combination is for some finite subset W. Finite. So call this W1, W2, so on till Wn. Now take linear combinations of vector in this. So the only difference between linear combinations here and linear combinations that we took earlier was like, we actually began with a finite set when we wanted to take linear combinations, or like even though the vector space was infinite, not infinite dimensional, okay, even though the vector space was infinite in cardinality, whenever you wanted to take a linear combination, we just pulled out a finite set and then we took a linear combination as we wanted. But here this basis B is an infinite set by itself. Okay, so the set that we pulled out is still infinite. So what we'll say is like whenever you want to take a linear combination, pull out a finite set and then take a linear combination over this finite set. So linear combination is only defined on some finite subset of whatever set we want to take. Okay, so this is the only catch here. Otherwise things are fine. Is this clear, folks?
Yes.
So just to be clear, if the basis is infinity, look at finite subsets and then look at linear combinations of those finite subsets.
No, sir, you're barely audible.
I had a doubt. If
Uh,
we don't take the whole of B, then how can we call it a basis? It is not minimally spanning set.
no, I'm not claiming W is a basis. What I'm claiming is give me a basis B. What does it mean to take linear combination of vectors in B, right? So I can't take alpha I vi for every vector I belonging to B and then take an infinite sum. I'm just saying a linear combination must look like like finite sums. But when you take linear combinations, right, like it need not always be over the same subset W. So this is one valid linear combination. There can be another valid linear combination of this form, alpha 1 prime w1 prime plus so on till alpha n prime, sorry, w alpha m prime w m prime for a different subset w1 w2 so on till wm of B. So how do we define linear combinations, right? Like pull out some favorite subset of yours and then take linear combination over that finite subset. You can pull out multiple finite subsets and take linear combinations. Those are all fine. Okay, is that clear?
Yes, it is.
Okay, good. Okay, any more questions? Otherwise, we'll quickly write the summary.
So can you give an example of an infinite basis?
An infinite basis. Well, so we said real numbers is the vector space over rational numbers, right?
Yes.
Okay. So now how will this infinite basis look like? Well, first you need to cover all rational numbers. So you'll add 1 to it and then maybe add root 2, root 3, root 5, root 7. So add all such guys. I mean, this is a very terrible way of writing this because this cannot be enumerated, okay? And then you'll have to cover for pi, e, the golden ratio. No, the golden ratio is covered with 1 and root 5. And then so on. So you'll actually have to cover all such possible linearly independent real numbers which cannot be expressed as linear combinations of others, right? So real number as a vector space over Q actually is infinite dimensional. Does this make sense?
Yes.
Okay, good. Cool. So now we'll look at the summary, or if there are any more questions, I can still delay the summary for a bit. Or once again, you're all free to hang out after the lecture. I'll hang around for 5-10 minutes and
Sorry,
then.
can I just? So I would
Yeah.
not want all of you to stay back. I just want to discuss something with you, so nobody leaves after the session immediately. Yes, now you can continue. Yeah.
Okay. Yes. So the summary. So what did we first show? We said all vector spaces of dimension n over the same field f are the same up to isomorphism. Very loosely putting this, all linear operators are essentially matrices. This also implies the space of all linear operators has dimension m cross n. Oh, this linear operator is from B to B prime with dimension n and dimension m. And then the last important thing that I would want to carry from this lecture is this notation: f to the set S is a collection of all functions f from S to F. So is the vector space is a representation of the of vector space. Of space of, I mean, loosely speaking, once again, cardinality of S. So if S is real numbers, then I mean we can't really call it the cardinality of real numbers, but it just says, you know, an uncountable, infinitely large set which is in bijection with real numbers. Cardinality of S as cardinality of S coordinates. Cool. So this is going to be the summary of this lecture. I mean, after Vinay's announcement, feel free to hang around if you have any questions. Okay. Cool.
Yeah, when I said is rejoining, it
Mhm.
will be there in our
You might also want to stop the recording. Say.
Yeah. I am not the host now, so I won't be able to do that.
Yeah, let me make you the co-host. Is that okay? Or you want to be the host?
No, no, no. I just wanted to stop the